Okay, for 4B, we're going to look at applications of our linear and exponential modeling. So we saw in the Module 2 project a question similar to this. We're looking at different types of interest in accounts. So there are two different types of interest that we're going to talk about. There's simple interest and compound interest. In general, interest is going to be the amount of money that you pay to borrow money or the amount of money that you earn on a deposit. So if you're putting money into a bank, the bank pays you an amount in order to use your money. If you're taking a loan, which we'll talk about later, then interest would be how much you pay in order to use the bank's money. Your principal is going to be the amount of money on which interest is paid. So normally it's going to be the original amount that you borrow from a loan or the original amount that you put into an account. Simple interest then is only going to be interest paid on the original principal, and not any interest added at later dates. So every year you're going to get the same amount because it's going to be based on what you put in. Compound interest, though, does include the interest that they put in. So the bank would put interest into your account, and then that becomes your new principal, and they give you a percentage based on that amount, and then they put into your principal, and so on. So the interest compounds on each other. So the simple interest, since you're going to be adding the same amount each time, that is going to be a linear relationship. And so it's going to follow along the lines of y equals b plus mx like we've been doing, but instead of using those letters, we're going to put something a little more specific to our circumstances. We're talking about money and lending and investing money. We're going to use different letters. So instead of y, we're going to have a, and A is going to be our accumulated balance. And then my starting amount, that's going to be your principal, the amount that you originally put into the bank. So your P is going to be your principal, or your beginning amount. And then the amount that you moved, your change, your slope, that is going to be the amount of interest that gets put into your account. Now, in the previous module, we always had, we would either have points given to us to find the slope, or we would be given the rate. In this case, we're not given the actual number that it increases or decreases by. Instead, we're given a percent. This is one of those cases where it's a percent of something, which makes it linear rather than a percent increase. So to find that number, we have to find the percentage of that principal. So you take your APR, so that's your annual percentage rate. You change it to a decimal. And so your interest is going to be the that percentage rate of your principal. So you take your percentage rate of means times your principal, and that gives you your slope. And you're going to add that for y number of years. Okay, so that is my linear. Of course, this P plus APR, if you ever want to just find the amount of interest annually, that is all you would have to do. You do the P times APR and you get the amount of interest that gets paid annually. Now, if you don't want to remember as P as this, if you don't want to have P written twice, you can factor out the P and you get P times 1 plus APR times Y. But that's your option if you want to do that. Now the key word when you're looking at problems to say whether it's a simple interest, it will have the word simple in there. If it doesn't say the word simple, it's probably not going to be simple interest. So when it gives you that APR, it will say if it's simple or compound. So let's look at an example. So let's say we want to calculate the amount of money you'll have after 5 years, assuming that you earn simple interest. So here we see the word simple, so we know we're going to use that linear model. So you're going to deposit $1,500 in an account with an annual interest rate of 4%. So if we're going to use our linear skills, we need our beginning and we need our end. So our beginning, right, is going to be 1,500, and our slope is going to be our a certain percentage of what I make. So it's APR is 4% out of 1,500. So we have 4% times 1,500, which is, I have that written down, 60. So just by using our linear skills, we can say that the ending balance, our y, is going to be equal to 1,500 plus 60x, where x is going to be the number of years and y is your accumulated balance. Now using these terms, I'm going to use a slightly different method, but again, you can take this or you can just stick with the b and the m. But using our things, if you want to memorize this formula, what I like to do is I like to write out all of my variables and fill in what I know. So in this case, A is accumulated balance. Well, in this case, they don't give us the accumulated balance, but that's what they're asking for. So that is going to be our unknown. Our principal, what we deposit, is 1,500. The APR they give us is 4%, which is 0.04 as a decimal. And it says in the problem that we want to have after 5 years. Now for the actual equation then, we plug in what we know. So we have 1,500 for a percentage. And if we do our combined one real input percentage once, we have 1 plus percentage rate times the number of years, which in this case is 5. And you can put that all in your calculator once. So 1,500 parenthesis 1 plus 0.04 times 5 parenthesis, and we get 1,800. Now you could also use our equation that we found here, right? Because we wanted it after 5 years. So our y would be 1,500 plus 60 times 5. Which also be 1,800. So you can pick which method you want to do. If you want to use this formula, if we just want to remember y equals mx plus b, you can do it that way. For simple interest, it is completely up to you. Compound interest gets a little bit more complicated. Compound interest is your exponential. Right, so this time interest is getting added back onto your principal. So we're not adding the same amount every time. That amount is actually going to increase every single year. So in that case, it becomes exponential, right? So our previous formula was Q equals Q naught times 1 plus R to the T. Notice the same thing, we're just using different letters. So instead of Q, we have our accumulated balance. Instead of our Q naught, we have our initial principal, the initial amount that we put in. Our rate is now our APR. And for T, we have Y. So all of these mean the same things we did before. The key word for these problems is the word compounded. And to use this equation, you have to make sure there's only one single deposit. If you make multiple deposits, right, it's going to mess with your balance. And so the percentage is going to be different. So we'll deal with that in a minute, but for now, we're just going to use our basic exponential equation because we're only putting in money once and we're just going to let it sit and increase. So in this first example, let's actually compare simple and compound interest to show how it works. So just to verify if you want to verify they are linear and exponential. So we can look at Ariel and Travis. So Ariel is going to have a simple interest account and Travis is going to have a compound interest account. So let's look at Ariel. So let's look at, for the first 5 years, how much interest she gets annually, and then how much her balance is at the end of every year. So Ariel is going to deposit $5,000 in an account, earning interest at an annual rate of 3%. Remember, this is simple, so that means our beginning is 5,000, and our slope is going to be percentage. Can't have a percentage by itself, so it's a percentage of our original balance, which is 150. So if we're going to have an equation, then we say y is going to equal my initial plus my slope times the number of years. So the annual interest, right, for simple interest, the annual interest is always going to be the same. So every single year, she's going to get $150 put into her account. That's the nature of being linear. So if she starts at 5,000, 1 year later she adds 150, so that becomes 5,150. Then you have to add another $150 of interest, so that's 5,300. Add another 150, that becomes 5,450. Another 150, you get 5,600. Another 150, you get 5,750. So after 5 years, Ariel would have $5,750 in her account. Now for annual interest for Travis, because it's compounded, that's going to be your exponential. So again, if we want to use the original equations, we can do that. So our Q naught, our initial, is going to be 5,000. My rate is going to be 0.03. So we'd have Q is equal to 5,000 times 1 plus 0.03 to the t, where t is the number of years. So we can use that to fill in Travis's balance, but we can also look at figuring out what his annual interest rate is. So the annual interest rate is always going to be 3% of whatever it was before. So for the first year, it's going to be 3% of the 5,000 that he first put in, which is going to be 150. So that first year, he gets the same amount. Now this interest gets added to his balance, so that becomes 5,150. Okay, so just like Ariel. But here comes a change. So while Ariel stays at 158 every year, Travis is now going to get 3% of his current balance, which is 5,150. So this time he's going to add 154.50. So he'd have 5304.50 after that. So you can see after 2 years, Travis has an extra $4.50 that he didn't put in. Okay, so again, the next year you're going to take 3% of what the current balance is. And that gives you 159.14. Now I am rounding here when I write this on there. One caution if you're doing this on paper or on your calculator is always use the actual number. So if I did like the 0.03 times 5,150, does give me this exact, which is fine. But when I take this and multiply 0.03, I end up getting I'm getting 159.135. So on paper, I'm rounding it, but I'm going to use the exact number in my calculator. So I'm going to take that 159, and I'm going to add that onto the 5304, and I get 5463.64 rounded. But in my next calculation, I'm going to take 3% of that. I'm actually, in my calculator, going to use the exact amount. So I'm going to just leave this in my calculator, and I'm going to type times 0.03. On your calculator, you should see A and S times 0.03. You hit enter, and that should give you 163.90905, which rounded is going to be 91. So I'm going to add that. This time I'm just going to leave the exact number, or the rounded number here. So 5463.64. 55 rounded. So again, I'm going to do 0.03 times that answer. To get 168.83. And I'm going to add that on to 5627.55. So at 5796.38. So after 5 years, Travis would have 5796 in his account, whereas Ariel only has 5750. So it's an extra $46.38 that Travis didn't have to put in, but he has in his account. Okay, so this is finding it, step by step. We could also have found this balance using our formula, right? So we did that in the last module. For the year 1, we put a 1 for T. For year 2, we put a 2 in for T, 3 in, 4 in, 5 in, and that way we don't have to worry about all the rounding stuff in the middle. So in general, we can see that compound interest is always going to be greater than simple interest, except for that first year. The same percentage, the first year is going to be the same, but otherwise compound is better. And that is just because the interest in simple interest is only on your principal, whereas for compound, it's going to be on the principal and the interest. So you get interest on your interest, which is awesome. Now, of course, things don't always just get compounded yearly. Sometimes they get compounded at different intervals. So when this happens, we have to kind of adjust the formula to match. So instead of just having one interest rate, we're going to take our yearly and we're going to divide it into the number of times that it gets compounded. So we're going to call that N. So N is going to be the number of times the account gets compounded in 1 year. Okay. So for example, if it's annually, that means it only gets compounded once a year. So my N is going to be 1. If it's compounded monthly, there's 12 months in a year, so it's going to get compounded 12 times. If it's quarterly, there's 4 quarters in a year, so there's 4 times it gets compounded. For daily, it is going to get compounded 365 times. So for our formula, instead of writing yearly, since it's now going to be compounded every a different amount, then we're going to have to divide that yearly into that many accounts, or that many time periods. So we do APR divided by N, and then the exponent, instead of saying the number of years, we're going to say the number of times it gets compounded in a year. So we can call this your periodic rate, and this is going to be the total times it's compounded. So when it was just once a year, you just multiply, you just raise it to the number of years. Whereas if it is a different amount, it's going to be according to how many times a year it gets. And so you take the number of times per year times the number of years to get the total number. Okay, so essentially you're answering this question: what is my balance if P is deposited or invested at an APR of some percent, compounded N times per year for Y years? Okay, putting this in your calculator, you can put it in all at once, but what I suggest, because of something we're going to come up with later, is that you first calculate just the interest part of it. So ignore the principal and just start from the parentheses, and put all that in first. So you have parenthesis 1 plus your APR as a decimal, divided by your N, parenthesis, caret to say you want it in the numerator or in the exponent, and then you parenthesis N times Y, parenthesis, and enter. Once you do that, then you're going to multiply by the percent. And the way I'd like you to practice doing it is to type in your P and then multiply and then press the second button and then answer. And answer is on top of your negative button, and then you hit enter. And this just saves us, you only have like, it just helps with a future problem. So we're going to practice it this way. Okay, so another example. So suppose that 5,000 is deposited in a savings account at the rate of 6% per year. Find the total amount on deposit at the end of 4 years if the interest is the following. Okay, so we're going to compare these different ends. Okay, so if it's simple, that's just what would be your linear. So for simple, you're going to start with 5,000. And then each time you're going to increase by a certain amount, and that amount is going to be 6% of your deposit. So 0.06 times your deposit, which is 300. So my account at the end of the year is going to have 5,000 plus 300 for each year, and they want to do it for 4 years. So we have 5,000 plus 1,200 to give us 6,200. So in a simple account, I would have 6,200 at the end of 4 years. Now annually, when it's compounded annually, n is going to be 1. Our principal is 5,000. Our APR is 0.06, and my Y is 4. Okay, so my exponential, right? You start with your original amount. So the original amount is our principal, which is 5,000. And so 1 plus your rate. Now this is just one time per year, so it's going to be 0.06 divided by 1. So in other words, like because it's the entire year, you're going to have that full 6% when you compound it. And that is going to be raised to 1 time per year times 4 years. So you have 1 plus our APR over n raised to the n times y. So in my calculator, I'm going to start with this. So I do parentheses 1 plus 0.06 divided by 1 raised to the 1 times 4. So we get 5,000 times 1.26248. Okay, but I'm not going to round up my calculator. I'm going to keep that. So I have this showing in my calculator now, the 1.26248. And then I'm going to type in 5,000 times second answer. So I do 5,000, the times button, your second button, and then the answer, and enter, and you should get 6312, 38 rounded. So for compounding annually, you get $6,312.38 at the end of the year. So already you can see that, or at the end of 4 years, sorry, you can see that the simple and annually are, a fair bit apart. Okay, semi-annually. So semi. You can think about like semi-trucks. You can think about semicircles. Semicircles is probably a little easier. So a semicircle, right, is half of a circle. So semi-annually would be half of a year. So it's going to get compounded every half year, so which means the total number of times it compounded in a year is going to be 2. Okay, so my P and my APR stay the same, and my Y. So this time the only thing different, so I still start with 5,000, and my rate is 0.06, but this time it gets compounded twice. So I need to take my yearly rate and divide it by 2 to get the rate for each half of the year. And it's going to be You're going to do this 2 times every year for 4 years. So again, you're going to do this part first in your calculator, and then you're going to type in 5,000 times that answer. And you should get 63.3385. Compounded quarterly. So quarterly, like there's 4 quarters in a dollar, right? So there's 4 quarters in a year. So we have 4 times each year. So this time we still start with 5,000. This time my annual rate has to split up into 4 different periods. So I'm going to divide it by 4. And it's 4 times a year for 4 years. And then you can put that in your calculator and you should get 63.4493. Compounded monthly. So there's 12 months in a year, which means it's going to be 12 times each year. So my A is now 5,000 times 1 plus my annual rate divided by 12 periods. 12 periods a year for 4 years. In other words, it's going to be compounded 48 times. So it's going to have to multiply those 48 times. And that's how our exponential function works. Putting this in your calculator, you should get 63.5245. And lastly, let's look at compounding daily. So there's 365 days in most years. So we'll always use the 365 for generality's sake. So our ending balance, we're starting with 500. We have 1 plus our rate. So our yearly rate is 0.06. To get it into a daily rate, we divide it by 365. And it's going to be this is going to be done 365 times each year for 4 years. And for that, we get 63.5612. Now notice as our n increases, to go from simple to 1, 2, 4, 12, and 35, 365, our balance is increasing. So from this, we see that shorter compounding periods which means you have a greater n value, is going to result in large money over time. Right? So the more times you can compound your interest, the quicker it increases. Okay, an example. Compute the balance in the following accounts after the stated period of time. So part A, 4,000 is invested for 5 years with an APR of 3% and daily compounding. So it does say compounding, which means we know it's not going to be simple. It's daily compounding. Okay, with an APR of 3%, invested for 5 years, and 4,000 is invested. So just as a summary of what we have, so we have our principal they give us is 4,000. We're investing it for 5 years. Our annual rate is 3%, so 0.03. Daily compounding says that n is going to be 365. Okay, and they want the balance, so they want to know A. In fact, you're always going to be either given A or P. If they give you P, you have to find A. If they give you A, you have to find P. So they give you P. So my A, following our exponential rules, we start with what we start with. So we're going to start with our initial principal of $4,000. And then it's going to be 1 plus our rate. So our annual rate is 0.03, but we're not compounding annually, we're compounding daily. So we need a daily rate, so we convert that, you can say, to a daily rate. So we 0.03 divided by 365. And it's going to multiply that percentage 365 times a year we're saying for 5 years. So put this in the calculator. Again, start with the parenthesis, do all that, and then do 4,000 times second answer. And we get an ending balance of $4,647.31. Now for part B, we have $10,000 invested for 5 years, then an APR of 2.75% and monthly compounding. Okay, it says compounding, so we're going to use exponential. So listen information. It starts with $10,000 invested, so that is my principal for 5 years. So again, we're looking at a Y of 5. Our APR is 2.75%. Remember, you move the decimal place over 2, so that becomes a 0.0275. And monthly compounding says it is, that end is 12. So plug it into the formula. Now you will have most of these formulas on a formula sheet for the test, but if you can remember it without it, it'll be quicker for you. So our exponential, we start with our initial value that we input, and then it's 1 plus our rate, 0.0275, divided by the number of times per year. That's going to be raised the number of times per year times the number of years. And then we put that in the calculator and we get $11,472.21. Okay, so in this account we'd have over $11,000 in the account after investing $10,000. Okay, now let's say we have $25,000 invested for 30 years with an APR of 3.7% and quarterly compounding. Okay, right, we have $25,000 invested, so that is my principal. We're investing it for 30 years. And our APR is 3.7%, so it's 0.037. And quarterly compounding says my N is 4. So I have 25,000 to begin with, and I'm going to multiply that by my interest increase. So we have 1 plus 0.037 divided by 4 times per year. We have 4 times a year for 30 years. And we get $75,472.89. So we have tripled the money that we have after 30 years by not doing anything, just letting it sit. Okay, now comes the part where how we practice writing these in is going to come in handy. So let's say you care about how much you have at the end. So far we've said, okay, if I have this much to invest, how much will I have at the end? Well, let's say we want a specific amount at the end. So for example, suppose you have a new baby and you want to make sure that you have $100,000 for his or her college education. Assuming your baby will start college in 18 years, how much money should you deposit now? Now we know how much we want at the end, so we want to know how much we need to start with in order to make sure I have that. So essentially we're just doing a backward interest problem. So we've done this before in certain things, especially with percentages. So essentially when we're going backwards, we're just going to reverse an operation. So instead of starting with P and finding A, we're going to start with A and find P. So before we did P times our interest calculation, but this time we're going to do A divided by my interest calculation. So this is why I had you practice it doing in these 2 steps, because the first step is going to be exactly the same. You're going to do that, the 1 plus whatever, and then you're going to do A divided by that. And the reason we do that, we'll see in this example. So suppose you put money in investment with an interest rate of APR equals 3% compounded monthly, and you leave it there for the next 18 years, meaning you're not going to put more money in. You're just going to put that single deposit, which tells us we can use the equations we have. How much would you have to deposit now to realize $100,000 after 18 years? So in this case, you want to have $100,000 at the end, so we have A instead of P. But we still have an APR of 3%, so we still have our APR is 0.03. compounded monthly, so we have our n is 12, and we're letting it sit for 18 years, so our y is 18. So if I were to plug it into the equation that I have, because I have a, I have to put it where a was. I don't know p, so I have to leave it as p. And then 1 plus our rate divided by the number of times per year, and raise that to the number of times per year times the number of years. So now we can't put it in all at once because we don't have a number for p. Do not put $100,000, 100,000 times all of this, because that is just ignoring this negative or this equals and this p, right? We can't do that. So instead what we're going to do is we're going to calculate this first, just like we did before. So this 1 plus 0.03 over 12 comes out to be 1.71485 and some more after that. Now, you can write it all out, but again, I recommend just leaving it in your calculator and then just doing, whereas before we did p times that, now we're going to do a divided by that answer. So 100,000 divided by that 1.7 and so on, and you get an answer of 58, 3, 14, and 11. So you're starting with the end, so you're going to divide. Just like with percentages, if you start with the beginning, you're going to multiply. If you start with the end, you're going to divide. So if we want to have $100,000 in this account after 18 years, today I would have to deposit $58,314.11. Now, another example. How much must you deposit today into the following accounts in order to have $25,000 in 8 years for a down payment on a house? Assume no additional deposits are made. And this is the key here, which tells us that we're going to use either our linear or exponential equation. So for A, we have an account with quarterly compounding and an APR of 4.5%. So here we have compounding, which means we're going to use our exponential. List down the information we have. So we know that we want to have $25,000 at the end. So we know our A is going to be $25,000. We're going to let it sit for 8 years. So my year is 8. Nothing else in the original instructions. So we have an account with quarterly compounding. Quarterly compounding tells us our N is going to be 4. And then we have an APR of 4.5%, which is 0.045. So we have our ending amount is going to be our principal times 1 plus my annual rate divided by the number of times per year. Raise the number of times per year times the number of years. So that's 8. Again, you're going to find this first. So we have 25,000 equals P times 1.3, sorry, not 1.3, 1.43045 and so on. And then you do 25,000 divided by your answer, and we get $17,477 even, rounded. So that means that to have $25,000 in 8 years, today we'd have to put in $17,477. Okay, now let's look at an account with daily compounding and APR of 4%. So same thing, we still want to have $25,000 in my account. And I'm still waiting for 8 years. But this time I'm doing daily compounding, so my N is going to be 365. And my APR now is 4%, so 0.04. So now my A is going to equal my P times 1 plus my rate divided by my N raised to the N times Y. again, we're going to do this first. And we get 1.37710 and so on. Then we do 25,000 divided by that answer. And we get $18,154.04. In this case, this first one would actually be better because we wouldn't have to put as much money in at the beginning in order to have the same amount at the end. Okay, example 7. Again, looking at your college fund. How much you deposit today into the following accounts in order to have a $120,000 college fund in 15 years. Assume no additional deposits are made. So again, this is going to be our ending amount. So that's what we want to have. In order to have 120,000 college fund in 15 years. So that tells you that this is going to be your A. Assume no additional deposits are made. Again, tells us we can just use linear or exponential. Because we're compounding, we know we have to use exponential. So again, put in our information. So we want to have 120,000. So our A is going to be 120,000. We're still letting it sit for 15 years. So my Y is 15. My APR is 5.5%, which is 0.055. Compounded daily means my N is 365. So my A is going to equal my P times 1 plus my rate over my N raised to my N times my Y. Okay, so I do the same thing I was just doing, and you should get $52,591.47. So for this count, you have to deposit $52,500 in order to have that college fund in 15 years. Now let's say we have an APR of 3.5% compounded monthly. So smaller APR, but more often. Let's see how that affects it. So again, we still want 120,000 in our account. We want to do that after 15 years. This time my APR is 0.035 and my N is monthly, so it is 12. So 120,000 is going to be your P times 1 plus your rate. The annual rate divided by the number of times per year, 12. And the number of times per year times the number of years. Finding the interest rate and then 120%, or the interest amount divided by 120% divided by that, and you get $71,040.91. So it's compounded more often, but the APR is makes it so you have to have a higher deposit at the beginning. So let's do another comparison similar to that. Let's look at Rosa and Julian. So Rosa is going to invest $3,000 in an account with an APR 4% annual compounding. Julian is going to invest $2,500 in an account with an APR 5% and annual compounding. So he's going to put less in, same compounding but higher percentage. So let's look at each of their accounts after 5 years and 20 years. So I'm going to set up a little table here. All my Rosa calculations I'm going to do on the top, and then Julian I'm going to do at the bottom. So writing down the information they give us for each person. So Rosa is going to invest $3,000. So that tells you that is your principal. So principal is going to be $3,000. It has an APR of 4%, so her APR here is 0.04. And annual compounding means your N is 1. Okay, Julian invests $2,500, so his principal is $2,500. An APR of 5%, so his APR is 0.05. And annual compounding, so his N is also 1. Now we're going to compute the balance in each account after 5 and 20 years. So let's say my Y is 5. So it's going to be 5 for both of them. So plugging it into the equation, because it is compounding, we're going to use our exponential. So our ending amount is going to be our principal times 1 plus our annual rate by the number of times per year. There's 1 time per year for 5 years. And we get a balance of $3649.96. So $3,649.96 after 5 years for Rosa. Well, for Julian, he deposits $2,500, but his interest rate is 0.05 for 1 year. Raised to 1 year times, or 1 times per year times 5 years. Sorry, I'm going to rewrite that so it's a little bit easier to read. Start it a little bit further down. So we have A equals 2,500 times 1 plus my rate divided by 1 raised to the 1 times 5. Okay, so Julian after 5 years would have $31.90.70. So if we're just looking at 5 years, it looks like Rosa has the better option, right? Because she has 36 and Julian only has 31. But let's look at 20 years. What does 20 years do? So Rosa after 20 years, again, she starts with 3,000. 1 plus my rate over 1 time per year. 1 time per year times 20 years. So after 20 years, Rosa has $6,573.37. Now let's look at Julian. Julian, so he deposits $2,500 at an interest rate of 5% per year, 1 time per year, raised to the 1 times 20 years. And he has $6,633.24. So that in 20 years, Julian has more money than Rosa. So another way we can compare it, so we can say that, okay, after 5 years, Rosa is better. After 20 years, Julian is better. And so you can say that, for short term, maybe the higher principal makes a difference, but in the long term, the higher interest rate makes a difference. But we can also look at the percentage, the makeup of your amounts. We can talk about the amount of return, which basically means how much of your ending account did the bank put in versus how much did you put in. So we're going to look at percentage of the balance that is interest. Notice that we have the words is and of. We don't have any comparison words. So we are going to use our part out of a whole. So we put our is over our of. So it's is interest. So that means we're going to have interest in our is, and it's going to be divided by the of the balance. So to find that percentage rate, we're going to have to take our interest and divide it by the balance and then convert to a percentage. So again, we're going to have to find information for both Rosa and Julian. So after 5 years, Rosa, we want the total amount of her balance as interest and divide it by the total balance. We know the total balance is $36.49, right? So how do we figure out the total interest? Well, your balance is made up of 2 things, right? The money that you put in and the money that the bank puts in. So we know that your balance is going to equal your principal, the money that you put in, plus the money that the bank puts in, which is called interest. So there's a couple different ways you can do this. So you can figure out the actual interest number, because you know that these 2 add together to make this. So if you know one, you can find the other. So if we know the amount that she puts in, and compare that with the amount that they had at the end. So at the end, she had $36.49.96. But if you subtract off the money that she put in, then you have the money that the bank put in. So that's $649.96 is the amount in interest that she got. So once we have that, then we can put that interest amount, $649.96, and divide it by the total balance. And we get 0.178 or 17.8%. So after 5 years, 17.8% of Rose's balance was just interest. Okay, looking at Julian. So his balance was $31.90.70. He put in $2,500. So the amount of interest that he got, can't do that one in my head. $31.90.70 minus $2,500 gives me $690.70. So that's the amount of interest that got put in. So we take the amount of interest and divide it by the total balance. And we get 0.21 or 0.216, sorry. And so that would be 21.6%. So we can see that even though Rosa had more money in her account, Julian actually had the better return. So more of his balance was just interest than was Rosa's. Okay, let's look at 20 years now. So 20 years later, let's see the breakup. So this time I'm going to do it a little bit differently. So first I found the interest and then found the percent. This time I'm actually going to use the fact that the percent of that is interest. The percent that is interest plus the percent that is your principal is going to make up your total percentage, right? Because those are the only two things that are in your account. And so in this case, this time I'm going to find the percent first, and then I'm going to subtract it from 100%. So at first I did the subtraction to find the interest. This time I'm going to do the division first and then do the subtraction. You can do whichever way you feel most comfortable with. So if we're going to define the percentage first, well, I don't know the interest, but I do know the principal. So for Rosa, she put in $3,000 out of a total of $36.49.96. So if I find that first, so I find 3,000 divided by 36.49, that should give me a 0.822. Right? Oops. 649. Yeah, 0.822 rounded, which is an 82.2%. So I know that 82.2% of this is the principal. So to get the interest, I'm going to take 100% minus my 82.2. And I get my 17.8%. Oh, you know what? So that's what it would be if it was for 5 years. But of course, we're trying to find our 20 years. So well, you can see that the calculation would be the same. You both get the 17.8 if you were talking about the 5 years. But we're talking about 20 years. So in 20 years, Rosa still only puts in 3,000. But her balance after 20 years is 65.73.37. So we're going to take 3,000 divided by 65.73.37, and we get 0.456 or 45.6%. So again, that is the amount of her balance that is principal. So to find the percent of the balance where it is interest, you're going to take 100 and subtract off the 45.6 to get 54.4%. So after 20 years, over half of Rosa's balance is just interest. So So again, for Julian, I'm going to do the same thing. I know that he put in $2,500 and he had $66.33.24 at the end. So his percent of the balance that is principal, so we get 0.377, so that is 37.7%. So the percent that is interest is going to be 100 minus that 37.7 to get 62.3%. So again, we see that Julian for both 5 years and 20 years has a greater return. So more of his balance is interest than is Rosa's. But in the short term, Rosa has more money in her account after 5 years than Julian does. So the questions you're going to get after one of these questions in MyMathLab is going to be usually like which one is better. And so sometimes it'll talk about the greater balance, sometimes it'll talk about the greater return. So if it's comparing balance, you're going to be looking at what we did for part A. If it's going to talk about a return, then it's talking about what we did in B. Okay, but in general, let's just comment on the effect of interest rates and patience. So we mentioned that we said that for 5 years, Rosa is better because she had the higher principal, but in 20 years, Julian is better because he has the higher interest rate. So in general, we can say part C, that a lower initial principal with higher APR over a long enough period of time can result in a higher balance than a higher initial principal with lower APR. And that is 4B.